Section 9.4 Passive Circuit Elements in Frequency Domain. I'm going to quickly summarize what Professor Aguilar mentioned and discussed about resistance, capacitance, and inductance in frequency domain. Specifically, if you take a resistance R, in time domain you know V is IR. But if you're interested in calculating the phasor voltage and the relationship between the phasor voltage and the phasor current, you will see that in frequency domain, the voltage is R times I, very similar to the Ohm's law. Similarly, for an inductor, the relationship between the phasor voltage across the terminals of the inductor and the current I flowing through the inductor is also pretty much the same. The voltage is J omega L times I. Now you can call this J omega L as the impedance, the L. It's called impedance of the inductor. Similarly, if you're just to look at the omega L component, omega times L component, that is called XL, or it is also called inductive reactance. Okay. Then, if you look at the capacitance in frequency domain, you will see how useful this frequency domain analysis is. Okay, a capacitance with voltage V across it and the current I. The relationship between voltage and current is that it is 1 over J omega C times I. Okay, where 1 over J omega C is denoted by ZC, also called the impedance of the capacitor. Similarly, 1 over omega C is called the capacitive reactance. Okay, now 1 over omega C is called the capacitive reactance. It's called XC, capacitive reactance. Now, that's all there is to it. What we want to understand and realize is in frequency domain, the same canonical structure of V equals to Z, some impedance times I, very similar to the Ohm's law applies. Ohm's law applies to only resistors in DC circuits or the circuits that we saw so far. However, in frequency domain, we can see the general structure of B is Z times I. Let's put that into practice. Let's look at an example. Okay, in the example, an inductor is given and the value of the inductance is given to be 20 millihenry. Okay, the value of inductance is given to be 20 millihenry. Similarly, the current is also given as a cosine or a sinusoid function. We are supposed to calculate the inductive reactance XL. Similarly, the impedance ZL, the phasor voltage, so that will be big V, okay? V prime. And then the time domain, you see, this is the time domain value of V, okay? So some calculations that have to be done, okay? However, this is a pretty straightforward problem. Let us see, how do you calculate? Let's begin with calculating XL, okay? We are interested in calculating XL, which is the inductive reactance, which is given by omega L, okay? Omega times L. We know L. L is given to be 20 millihenry. Do we know omega as well? Yes, we do, because omega is right there, okay? Because VIM cosine omega t plus theta or phi. That's the canonical definition of a sinusoid current, in which this 10,000 represents omega. So we can plug in a value for omega and calculate omega times L. You should see a value of 200 ohms for inductive reactance. Similarly, the second one we are expected to calculate is really ZL, which is the impedance, which is given by J times omega L, which is simply J 200 ohms. That's number two. Everybody with me? Pretty straightforward problem. Then we are supposed to calculate V, or the phasor voltage. But we do know V is what? J omega L times I, right? So in order to do that, we are going to change this I as a phasor form as well. Okay. Therefore, when we are calculating, so this can simply be written as V is ZL, where all of this is written as ZL times IL, or the current through the inductor. Okay. Now, therefore, V is, convert all of this into phasor form. Okay. In the phasor form, we have current to be current I to be 10 angle 30 degrees, J omega is 10,000 into this guy L, which is 20 millihenry. Okay, everybody with me? Let me separate them out a little bit more. So this guy is J, this guy is omega, this guy is L, this guy is I. You see, I expressed in its phasor form is 10 angle 30 degrees. 10 is coming from here, 30 degrees is coming from there. Okay, so very good. Now we have V new, okay, or VL across the inductance is simply, I'm going to write this guy in its phasor form as well. Think about it. If I write this guy in its phasor form, all of this is simply going to come out to omega L is I already calculated it to be J 200 ohms. So all of that J omega L, I just calculated that, did I not? So that guy is 200, J 200 ohms multiplied by 10 angle 30 degrees. Okay, now remember J, we looked at it, um, Aguilar mentioned it, and then I also summarized it. When we are looking at particular numbers, just J, it is 1 angle 90 degrees. You see, this guy, J1, is 1 angle 90 degrees. That's exactly what I'm going to do here. Okay, I'm going to transform this guy. Okay, I'm going to transform J200 into its phasor form or polar form, 200 angle 90 degrees. Okay, J is 90 degrees, 1 angle 90 degrees multiplied by 200. And then, of course, it's this 10, 30 degrees. Okay, here is the beauty. Okay, here is the beauty. And let's not forget this milliamperes here. Current is always in milliamperes because that is what is given. Okay, so all of this is milliamperes. So the phasor voltage is 200 angle 90 multiplied by 10 milliamperes angle 30 degrees. Here is the beauty of multiplying in polar form. All we have to do is to simply take a product of these magnitudes, then take a sum of these angles. Therefore, V is really 2 angle 120 degrees. Okay, so this is the polar form or the phasor equivalent. Now, that be your answer for your section number 3. Okay, now we are also asked to find out the time domain equivalent of this guy. The time domain equivalent is the inverse transform. So V of t is really 2 cosine 10,000 t plus 120 degrees in volts. This is the time domain equivalent. Where did I get this 2 from? Let me show. Oops, I wanted to. Uh, this 2 is here. Okay. Similarly, this 120 is right there. But where is this 10,000 T coming from? 10,000 T is coming from the current here. Okay. Current is given to be 10,000 T. Okay. Because these are linear circuits and they do not change the frequency, the omega t component carries through in all our calculations. So this guy, therefore, v of t equals to 2 cosine 10,000 t plus 120 degrees is the time domain expression. Okay, this is asked in problem number 4. Similarly, we calculated this to be problem number 2, and this guy to be problem number 1. Okay, therefore, the idea is pretty straightforward. It's a simple problem. There is another homework problem very similar to this on capacitance. I want to leave that as an exercise for you. Okay? Straightforward. What we have done is to go from time domain, take a phasor of it. Once we have a phasor, we should be able to multiply V and I, right? We should be able to multiply Z impedance and current to give us the voltage. Pretty straightforward problem. Okay.